we're going to demonstrate the equation of conservation of mass, which is one of the basic equations of fluid dynamics. This equation states that if you have a region where you have a flow of a fluid, mass should be conserved within this region, and you have important implications. Often it's also called continuity equation in some fluid dynamics books. But let's first imagine that we have region where fluid is flowing, and then we have a domain or a subregion within this region where you have flow of a fluid. If we consider this domain omega, this domain has a boundary which we call del omega. In this boundary we have a normal vector, which is a vector at any point perpendicular to the surface, and we have a velocity vector, which is a vector. It could take any direction here actually, but we're concerned with the component of the velocity vector that goes into the normal direction. So this is actually what counts for the flow of fluid through the boundary. Remember that this velocity vector here, if we're working on three-dimensional Cartesian coordinates, it has three components, u, v, and w, in the directions i, j, and k here. Okay, so this is basically stating that by the conservation of mass, the amount of mass within the domain omega will depend on the amount of fluid that is flowing through the boundary. This is pretty obvious because if you have more fluid coming in than going out, you're going to have accumulation of mass here, and if you have more fluid going out than coming in, you have a depletion of mass within this domain. So we're going to try to state this mathematically. First of all, what is mass? What is density? Density of the fluid in the case of the domain, or what we're concerned here, is mass per unit volume. So this is defines as the volumetric density of any substance that you might be concerned. So actually, if you have any domain here, we're talking about the domain omega, you have the volume of the domain, and the density is the amount of mass within this domain. You can also define this mass in the domain omega varying over time as the integral of the density over the entire volume. So the volume integral over the domain omega over volume here. This basically is stating that if I integrate the density at each point over the volume, if you remember, a density is mass over volume, and the volume is obviously volume. So this cancels here and you're left with the mass. So this justifies why the integral of the density of the volume is equal to the mass. But this is varying with time because the flow is dynamic. We're not saying that the flow is steady state, so it could also vary with time. So at any time, the mass within the domain omega is the integral over the domain, volumetric integral of the domain of the density of the fluid. X here is the coordinate system, so you can identify here each point by the directions x, y, and z by the coordinates x, y, and z over the directions I, j, and k. But now we can also state that this mass within this domain is varying with time. So the variation of the mass with time within this domain is caused or is influenced by the flow of the fluid throughout the domain and especially over the boundary. We can state that because the mass is the integral of density over the volume, we can state that the variation of the mass over time is the variation of the integral over the volume over time. Now what we need to do for further steps is to put this derivative here within the integral term. We're going to use for that the Leibniz integral rule. The Leibniz integral rule states that if you have the derivative over z here of the integral of functions of, so the limits of the integral are functions of z, of any function here of x and z over dx, is the integral from a to b of the derivative of a function dx plus a function of the upper limit here over z, derivative of b, the upper limit over z, minus the function of the lower limit here, a in z, partial derivative of a in z. This is stating that a and b are functions of z. But in the case in which a and b are constants, so the boundaries or limits of integration here are constants, this here wouldn't apply. This simplifies to just this first term here. This can be applied directly to this equation here, and we are left with this form here. So the derivative of the integral of density over the volume is equal to the integral of the domain over the domain omega of the derivative of the density with respect here also to the volume. Okay, so this is equivalent. This is equivalent to this, and this can be written as this term here using the Leibniz integral rule. So now we already know that the variation of mass over our domain omega here is the variation of the integral of the density over the volume. We dropped here the x coordinates and the t to simplify, because now we're working over the entire domain. So the variation of the mass on this domain can be equated to minus the density times the velocity vector dot the normal here over an area. So this here is an element of surface, so it's an element of surface of the domain, and now we're integrating over an area. What this means here, so we have, if you consider our domain here, you have the normal vector as before, and you have a velocity vector here, u, and we're concerned about the component of the velocity vector on the normal direction here, because this is going to give us the flow in this direction and the flow over the entire domain. But if you consider this term here, the density over the velocity, we already know that the density is mass over length cubed, and velocity is length over time, and an element of area here is L squared. So this L times L squared is L cubed, and L cubed cuts with L cubed. So this is saying that, considering that the outside normal direction here, because of this minus here, this is stating that the flow over an element of area of the surface, or over the entire area of the surface, is the mass per unit time. So this is saying that we have a mass per unit time flowing through the surface. And this whole thing here is saying that the variation of mass within the domain is equal to the amount of mass flowing in or out of the entire surface. This is pretty simple. If you have more mass coming in than going out, here over the surface, the mass is going to increase, the density is going to increase. If you have the contrary, the mass is going to decrease. But now we have an integral over a volume, and we have an integral over an element of surface here, or an element of boundary here, dA or del omega. We have to convert this integral here to an integral of volume. This is just stating that here we're using the form before using the Leibniz integral rule, and this is the one we're concerned after using the Leibniz integral rule. But now, same thing, we have to convert this here to an integral over the volume, and we use the divergence theorem for this. Divergence theorem here states that if you have an integral over a surface or over an area element of a function dot here, dot product, the normal over an element of surface area, it's equal to the volume integral of the divergence of the vector field over the volume. So we're applying this here to this term here, and we are left with the integral over the domain here of the divergency of whole u. So we just converted from using divergence term from a area integral, elements of area integral, to a volume integral. This here is a statement of an integral statement of the conservation theorem. So what we do now, we can equate this term here to this term here and replace it here over this integral statement of the conservation law. And we are left, as expected, with two volume integrals over our domain. Now what we do is we pass this term to the left side, so we have the integral of the density over the volume here is equal to the integral of the divergence of whole u over volume. We're left with the integral of omega over omega of the partial derivative of the density, variation of density with time in V, plus the integral of omega of the divergence of whole u over dV is equal to 0. So this is already starting to look like a conservation law. But now, because we have the same time of view integral here over the domain omega, and both are over dV, we can gather their terms and put the integral here outside. And now we have the statement which is seen in every fluid dynamics books. Every fluid dynamic book is the principle here of vanishing integrals. So because this statement here is true for any arbitrary volume here, any arbitrary volume, it must vanish everywhere. So because this is true for any arbitrary volume, this means that this term here inside it's equal to 0. It has to be equal to 0 for this integral to be equal to 0. Things that this needs to be equal to 0 because this is a conservation law. The amount of flowing through the area needs to be equal to the variation of the mass over the entire domain. So that for this conservation law to hold, this inner term here can only be 0. So if the integrand here is equal to 0, so the integral vanishes, we're left with the conservation law here, which states that the variation of density over time plus the divergence of whole u is equal to 0. You can write this in different forms, but in the end, what this is stating is that if you have a domain here, the amount of mass or the variation of the density within this domain is equal to minus wherever is coming through the surface. So if you think about this in terms of the divergence term can be interpreted as the velocity vectors here over the surface, in which they can be vectors going through outside the surface or to inside the surface. In this case, the density here will decrease over time, and in this case, the density here will increase over time, but the mass needs to be conserved. If the flux through the surface is increasing the mass inside, the density obviously increases, but if the contrary is happening, the density obviously decreases. And a very interesting special case of this conservation equation is when the density does not vary or when the fluid is incompressible. So in this case, we are left with the divergency of u equals 0, which is a very special case applied to incompressible fluids.